Hi, I'm here today because I recently found out that Silicon Soup has made another video referencing one of my videos. Now, I don't want to continue to flagellate this deceased equine, but in this latest video he showed something that I found pretty baffling, and I repeated his experiment and got the same result, and in the process learned something very interesting about toroidal inductors. So let's look at a little bit of background to get ready to show the experiment. This all started with Dr. Walter Lewin, a former physics professor at MIT, who referenced a paper by Robert Romar made in the early 1980s, I think 1980 or 81, in which he takes this circuit. And what we have is a solenoid or a coil of wire and some resistors around that and a couple of voltmeters. And we put some AC current into that solenoid, creating a changing magnetic field around which are these resistors and these voltmeters. And he analyzes what these voltmeters will read using Faraday's law and Maxwell's equations. And he concludes that these voltmeters, although they are connected to the same 2 points in the circuit, are going to read differently. Now, he finds that baffling, but as an electronics technician and any engineer would look at this and say, of course they're going to give you different readings, because they are not only reading the voltage across the resistors, but they are also affected themselves by the magnetic field. So nothing new to us, and several engineers, and including myself, made some rebuttal videos explaining why this happens and why it's not so baffling. But the other thing that Walter Lewin does is he says that this proves that Kirchhoff's voltage law does not always work. Now, I analyzed a circuit using Ohm's law and Kirchhoff's voltage law and came up with the same conclusion that Robert Romar did without using calculus, which is easy to do. But Walter Lewin also said that this circuit and the experiment proves that Kirchhoff's voltage law doesn't always work. And that is because we find that we have voltages across these two resistors, but no voltage in between them. Let me reiterate Kirchhoff's voltage law real quickly to see where he's coming from. Kirchhoff's voltage law says if we have a loop circuit, so I'll put a couple of batteries in here and some resistors, and I'm just kind of making this up as I go along. And I'll put another resistor here. And Kirchhoff's voltage law says that these voltages across these components must all add up to zero. To simplify that, I'm going to just make a simple circuit with a battery and a couple of resistors. So here's a battery. We'll put a couple of resistors over here. And we'll make this a 10-volt battery and make each of these a 5-ohm resistor. And here's our polarity across the battery. And we're going to have some current flowing through there, 10 volts and 10 ohms total. We'll have 1 amp of current. And then each of these resistors, of course, will have 5 volts across it, positive to negative. Another 5 volts, positive to negative. Now notice the sequence of positive to negative. We go negative to positive, so we gain voltage. We come around here, go positive to negative, so we lose voltage. Positive to negative, lose more voltage. And notice we gained 10, lost 5, lost 5. So the total is going to be 10 minus 5 minus 5 equals 0. So that's the basic idea of Kirchhoff's voltage law. However, sometimes people can become confused. For example, if we have a wire that is being affected by a time-varying magnetic field, we're going to induce some EMF in that wire, which is going to cause a current to flow. And that current's going to flow through a circuit if we make it a loop. And let's say we have that 1 amp again. Let's make this a 10 ohm resistor. That means we're going to have 10 volts across that resistor. We can read that with a voltmeter. But where's the other voltage of opposite polarity to counteract that? Well, of course, that is over here. So we have 10 volts of EMF over here. That is causing 1 amp of current. That's causing 10 volts of measurable voltage over here. And the argument is that, let's say this wire has 0 ohms of resistance. Well, we can't have 10 volts across 0 ohms because Ohm's law is violated. But they don't understand Ohm's law. Ohm's law cannot be applied to a part of a circuit that is the seat of electromotive force, meaning if there is electromotive force developing in that part of the circuit, you cannot apply Ohm's law to it. So Ohm's law isn't violated because we can't apply it to that. In fact, Georg Ohm found out that any resistance that is in this seat of electromotive force over here has to be analyzed in series with it. So there's where our 0 ohms is. And so we have basically, let me just erase this because it's becoming cluttered and a little confusing. We basically have a 10-volt battery in series with a 0 ohm resistor. No problem. Let me get a little plus to minus there. And so that piece of wire is simply acting like a 10-volt battery at any moment in time. Of course, if it's alternating current, it's acting like a 10-volt generator, but we're not going to get that complicated. It can be easily analyzed as this circuit. So A, you can't apply Ohm's law to a part of a circuit that is the seat of electromotive force. You can only apply it to parts of the circuit that are having voltage applied to them externally. And also, any resistance in there would be seen in series, so we can break that apart, and then we can apply Ohm's law to the two individual parts, and everything does work. Another way to look at this is, I'll pose the same problem with just a battery. Okay, let's make the original problem we just had. 10 volts, plus to minus, 5 ohms, 5 ohms, and we determined there would be 5 volts here and 5 volts here, plus to minus, and plus 10 minus 5 equals 0. That's Kirchhoff's voltage law. Let's combine these into a single resistor and see what happens. There's 10 volts there across that. Well, that's the same 10 volts that's across the battery. That's just like saying, well, I've got a wire here. Or let's make it the secondary of a transformer, because people are saying the same thing. If that has 0 ohms of resistance in it, there cannot be 10 volts across it. And therefore, Ohm's law isn't working, Kirchhoff's voltage law isn't working, everything's not working. But that's not the way either one works. We have here $10 negative to positive, and Kirchhoff's voltage law is a conservative situation where we gain potential and then we lose potential. So we gain 10 volts, then we lose 10 volts, ending up with 0. And if we go to the situation where we have a solenoid here with the alternating magnetic field in it or whatever, and if we put a broken loop of wire around there, we can read, let's say, 10 volts. Well, positive to negative, there's 10 volts, but there's no corresponding other 10 volts to counteract that. Well, yes, there is, because we gain 10 volts, then we lose 10 volts. So Kirchhoff's voltage law even applies here. Even if we could say there's no voltage across, or whatever we argue, we still gain 10 volts and lose 10 volts. So we're misapplying Kirchhoff's voltage law in the first place. So it's a moot point. So let's move on. Like I said, I'm kind of tired of this argument. They don't call it Kirchhoff's voltage law for nothing. It's not Kirchhoff's voltage theorem. It's Kirchhoff's voltage law because it has been proven time and time again. And I can find no peer-reviewed literature that says that Kirchhoff's voltage law does not apply in this situation. So I can argue till the cows come home. Dr. Lewin can argue till the cows come home. Silicon Soup and Electroboom and all of us who are arguing back and forth on this can argue till the day is done. And in the end, there's no peer-reviewed scientific literature that says that Kirchhoff's voltage law fails. So let's get on to what Silicon Soup found out. I'm going to start with my coil of wire. I'm just going to represent that as a circle because I have some wires coming in, going round and round and coming back out. So we're looking down the coil of wire. And I'm going to put a loop of wire around there. And so the way we've been doing this is we've been imagining that we're freezing time and there's a certain amount of current that just simplifies things. So let's say there's 1 amp of current flowing in there because at this particular time, the changing magnetic field subject to Faraday's law, is going to cause a certain amount of current to flow in there. But yet there's no measurable voltage in here because this is a non-conservative field. I explain all this in another video, which I've linked in the description below. However, if we break this, now the current can't flow anymore. So we have all these positive charges trying to fly over this way around the circle, and they hit here and they bunch up. And of course, it's taking them away from here, so we end up with a lot of positive charges here and very few over here. So we call that positive and negative, because is negative the opposite of positive? No, it's just a lower voltage than some other voltage. So higher voltage, lower voltage, we call that positive to negative. And there's going to be a voltage gradient along here. And there have been a number of experiments to show that this is true. Silicon Soup even diagrams it a couple of times. Here's one of them. And then here's another one where he uses a 2D and a 3D diagram to explain this voltage gradient. And then he claims it doesn't exist. But another YouTuber named From Jesse built this device that he called a Lewin clock that he set up so that he could measure the voltage around this loop without his measuring device being affected by the magnetic field. Notice that his probing wires are perpendicular to the circles of the coil so that they are not affected by the magnetic field. And there are other people who have done the same thing, and they do measure a voltage gradient around here. And I measured it without having to be quite so careful, because I have a solenoid, literally a solenoid, because it's a solenoid that's a coil of wire that used to have an armature inside it. This is my coil of wire, and then I have a loop of wire to go around it. And if I have that loop go around, I'm going to get a current in this loop, or an attempted current at least, which is going to skew my reading over in my oscilloscope. But if I take that broken loop and make sure that my wire does not go around the solenoid. So there's my measuring wires, but then the loop is going to come back this way. As long as I don't go around the loop, I'm not going to induce any current in these wires, and it doesn't matter what their shape is. In fact, Robert Romer even mentions that in his paper, that if we have a solenoid and we have a loop around it, we're going to get X number of volts. If we have two loops, we're going to get 2 times that. But if we have another loop out here, we're going to get nothing. And it doesn't matter what these shapes are. I'm going to get the same voltage with that shape, or the same current, as I do with the circular shape. And this other shape, it can be whatever you want, but I'm not going to get any current there because it does not circle the solenoid. So as long as I don't circle that solenoid, I am not affected by the magnetic field. So here I am measuring that voltage, and you can see I'm getting about 2 millivolts across this coil. And watch as I move the red lead. As I move it to the middle, I get a little less. As I move it down closer to the black lead, I get less and less. So there's clearly a voltage gradient along this part loop of wire. Of course, if I flip it around and have the loop go around the other side, then I'm not only going to be measuring the voltage on the loop, but also the voltage induced in the oscilloscope by the magnetic field, and I get a lot more voltage. But you can see that there is a clear voltage gradient along this loop of wire. So then Silicon Soup does another thing to prevent his measuring being skewed by the magnetic field. He used a toroidal inductor. So what's a toroidal inductor? I'll try to draw this here. You have a donut of ferrite material, and your coil is wrapped around that. And he hooked up his oscilloscope. Let me redraw this. Here's the, I'll just draw it like this. We're looking down from the top. There's the hole in the center. He has his wire going through here. He has his 2 black leads, or his 2 ground leads of his oscilloscope there. And he has one of the probes up here, and he has the other probe sticking down inside here. So there is our 2 measuring points. And since this does not go around the loop, it's going to measure the voltage gradient along that loop there. So how much is that voltage gradient going to be on his oscilloscope? Flat line, 0. No voltage gradient. That's awfully weird, but he has the other channel of the oscilloscope over here and shows a definite voltage across there, but no voltage gradient from there to there. And I found that very puzzling because several other people have shown that there should be a voltage gradient there. But this time he's using a toroidal coil, so does that make a difference? Well, I went to my electronic surplus store and got myself a little toroidal coil. It has plenty of windings, so I can get as much magnetic field as possible. And I repeated his experiment. So I did the same thing. And as you can see here, I do have a voltage across the ends of the loop, but as I measure around the loop, nothing. However, what I found out is if I measure, if I look at the toroid again, looking down from the top, and here's my loop of wire going through there. If I put my ground there and my probe here, I do get some voltage, some certain amount of voltage. But if I put my probe here, or here, or here, or here, or here, 0 volts. But if I put my probe here, or here, or here, or here, or here, or here, I get X volts. Okay, and there's no voltage gradient. It's just one or the other. Now in the video that I just recently saw, Silicon Soup did the same experiment again, but this time he put voltmeters all along here and showed that even though he got a voltage across the open loop, he got nothing along here. No voltage gradient. And as you can see, I'm repeating the experiment, trying at different places along the loop, and I'm getting no voltage unless I cross from one side of the toroid to the other. Okay, so what is that telling us? So let's redraw this again just to keep things simple on the board. Here's my loop of wire, and no matter where I measure, if I measure from here to here, I get a certain voltage. No matter where I put my probes, as long as I have one on one side and one on the other side, I get the same voltage. So if I move my probes from here to here, I get the same voltage as from there to there. But if I measure along here, I get no change. In other words, there's 0 volts. What does 0 volts mean? 0 volts is not the absence of voltage. 0 volts just means that one voltage is the same as another. That means that this voltage here is the same as that voltage there. And this voltage here is the same as that voltage there. And so all along this wire, I cannot measure any difference because that's what a voltmeter measures. It measures the difference in voltage. Same thing over here. But if my measuring loop goes through the toroid to my meter over here, then I get the same voltage as I measure over there. So what is that telling me? It's very puzzling. I have an EMF in here, then that should be pushing all of my charges to the ends of here, all my positive charges to here and all my negative charges to there. Keep in mind that I do talk about moving positive charges because when those negative charges move, if you could see them, it would look like positive charges were moving in the opposite direction. So we can talk about either charge, even though the positive charges are stationary, it looks like they move. So I would expect it to push the charges to the end, but it's not. So let's see if there's something that looks like. How about a battery with some wires on it? We'll make this a 10-volt battery. Well, we have 10 volts from there to there. And what's the voltage out here? Assuming there's no current flow and no resistors or whatever, I'm going to see with a voltmeter 10 volts. And we always assume that these wires have no resistance, even though they have a little bit, but we'll just ignore it. We always do when we do circuits. So if there's no resistance, I should not be able to get any voltage gradient across it. Well, I can if it's the seat of electromotive force, but it's not. The electromotive force is only in here. So I have 10 volts here. If I put my voltmeter, my black lead right there, now I'm going to put my red lead here. What do I expect that voltmeter to read? Positive 10 volts. What if I put it there? positive 10 volts. How about here? Positive 10 volts. How about there? Positive 10 volts. So I'm going to read the same voltage all along this wire because there's no voltage gradient on it. All of the voltage gradient is inside the battery here. So there's going to be a 10 volt difference between here and here, 0 volts up to 10 volts. And then since there's no current flowing, there's going to be no voltage gradient along there. Now, what's the difference with our original experiment? We have our changing magnetic field here and the open loop. Well, this entire loop is the seat of electromotive force, and so the voltage gradient goes along the entire loop. But all of the electromotive force is contained in the battery, so we only have the gradient inside there. So we have something that looks very much like that toroid. As long as we put our voltmeter from one side to the other, we're going to read 10 volts. But if we put it on the other side, if I put it here and there, nothing, 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 nothing. It's almost the same thing. Let me redraw that real quickly over here, just to remind us of what it's doing. There's our loop of wire, and between there and there I have a certain number of volts. So if I measure across there, I get voltage. If I measure there, I get voltage. But if I measure here, 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 and here, I get nothing. Here, 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 I get nothing. Over here, if I measure here, 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 or here, I get 10 volts. But if I measure here, 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 I get nothing. There, 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 I get nothing. So it looks like the same situation. So what am I to conclude by this? I can't find any literature talking about this. So far I've tried. But my best guess is that in a toroidal coil, all of the electromotive force is somehow contained inside the donut hole of this toroidal coil. So there is my total X volts there. So I can measure it out here. There, 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 and there. But of course, nothing there, nothing there, nothing there, nothing there. So it's acting very much like that battery. And so again, my electromotive force must be contained there. Unfortunately, there's no way for me to test this. Let's draw it a little bigger so that we can see how we might try to test it. So there's my core with my wires wrapped around it. There is my loop of wire. And of course, as we've shown, a certain amount of voltage here, no voltage there, 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 and there. So if I try to measure my voltage in here with the voltmeter, let's go ahead and connect it to the wire, what's going to happen? Well, this loop is going through the toroid, so it's going to induce voltage in there. So I'm not reading the voltage here to here, I'm reading the voltage that is developing across here because of the electromotive force pushing charges toward my voltmeter. So I can't read it that way, and the only way I can think of reading it is if I could put my voltmeter, let's say, here and there. Except I can't because I'm going to have a voltage induced there, positive to negative there, negative to positive there. So positive to negative and then back up negative to positive, they'll cancel each other out. So I'll still get 0 volts. So I have no way to test it, but my best guess is that the electromotive force is somehow confined inside this area here. I don't know what would cause that, but apparently that must be it because that's exactly what this is acting like. So that's what I've discovered about toroidal inductors. Somehow the EMF developed in this loop here is confined inside the coil and is not outside of it. And so the reason we don't read any voltage here is because there's no EMF out there. There's no voltage gradient because that is not the seat of electromotive forces. Nothing being induced out there. All of the EMF is being induced down inside here. How can I prove that? I don't know. Has this been studied? I can't find anything. Are there any physicists who have studied this and can tell me what it's doing? I don't know, but it is interesting. So, in conclusion, here is what I found out. If we have an open coil that we're looking down on the end of, and we have a loop of wire, I'll make this a broken loop. We're going to induce a current in there. That current is going to hit the ends. Charges will back up. And we will have a voltage that we can read there. But there will be a gradient of voltage. Higher voltage down to lower voltage, assuming the current is flowing in that direction. So voltage gradient along the wire. Highest voltage, lowest voltage. Why is that gradient there? Because this entire wire is the seat of electromotive force that's being induced by the changing magnetic field. However, if that inductor is a toroidal inductor, you do a little oblique view of it real quickly here. There's our toroidal inductor. There's our wires coming off of it. If it's toroidal, that means that all of the EMF is contained somewhere in there. How small, how big, I don't know. But all the EMF is somehow inside it. And if we have a wire going through there, there is no voltage gradient around here. It doesn't exist. All of the voltage gradient is inside that area there. So that is what I discovered about toroidal coils. I'd like to know if I'm on the right track. I'd like to find somebody who studied this and find something published about that. But so far I can't. So I hope this is intriguing to you as it is to me. And I hope you found this interesting and useful. And if you did, please give me a thumbs up. It really helps the channel. And if you want to help me keep making videos like this and finding these interesting things to look at, you can go to patreon.com/Vocademy and pledge your support. If you want to give a one-time donation, you can see the link in the description below. And a big thank you to my patrons for making this all possible, and thanks to everyone for watching.